Thank you everyone for making our time to be part of this class today. I know that most of us have busy schedules, but because of the value we put on this training program, we make out the time to be part of it. So it's not something that we take for granted. So I welcome you all once again. For the past about two Saturdays, my colleague Engineer Uche has been leading this presentation with economic and assessment of both energy efficiency and, of course, renewable energy projects. But today we're going to be talking about the renewable energy side of it, and specifically for solar system, solar PV applications and design. So as usual, I would like this to be interactive. If at any point you're not clear or you don't have a full understanding of what we're talking about, and you want to ask questions, please feel free to ask. You can raise your hand. You can stop me, and I will allow you to ask, and we can clarify. And also want to mention that I know some of us may have had some field experience, and so your experience is very important at work. If we get at some point where your experience sharing is needed, please do well to share your experience. Just to also encourage some of our colleagues, and also to make them understand that this is not just on documents, but rather these are the things that that are part of our day-to-day lives. Of course, I mean, electricity is something that in the modern age and the modern time, we nearly can, in fact, we can't do without electricity. Okay, so let's start. I mean, like I already said, we're going to be focusing more on solar PV systems. And so we're going to start from the very basic, which is the PV. A lot of times we hear PV. What does PV actually mean? So PV is a short form of photovoltaic. Photovoltaic, of course, photo means light, and then voltaic means voltage. I mean, so we combine it so it's more like so PV is or photovoltaic is the technology that generates electricity directly from the sunlight via the photoelectric effect. It may not be necessary for us to go into all the cells technology to design and execute projects. Okay, so the photovoltaic module to the grid. It can be stored in batteries, or for later use, or it can also be used directly. So let us explain this diagram that we have here, just to help us make sense of what I'm saying, right? So this is a PV module. In the presence of sunlight, it generates electricity, and this is assumed to be the load. And this load, let me also state here that the kind of electricity that is being generated by a PV system is what we call direct current, a DC current. There are two kinds of current. There's a direct current and there's an AC current, which is alternating current. What we mostly use in our buildings, industries, and offices is basically the AC current, that is alternating current. That's what we mainly use. But the PV system actually generates a DC current. So because it generates a DC current, then there is need for conversion into an AC current, and that's where the inverter comes in. As we proceed, we are going to look at different components, the modules, the inverter, the charge controller. But for now, just bear in mind that the electricity that is being generated from a PV module is DC, and they will need an inverter to transform it to an AC current. And if you go out in the market, this might be coming early. I mean, this what I'm about to say, but I just feel like it's necessary, and I just want to add it. When you go out to the market to buy a PV module, you see so many descriptions. You see so many ratings. So sometimes I think it's important that you understand what some of these things mean, even though it may not. Now, I'm trying to be careful because I know in the time past, after talking about this, I think somebody misunderstood this to be a type of PV model. We are going to come to that. So the point I'm trying to make here, when you go out in the market, you're going to see something like N-type, you're going to see something like P-type module, N-type module, right? Now, this is not a type of PV cell, right? However, it's just, the way it's being manufactured, okay? And because of that, the way it is being manufactured, it impacts on the efficiency of the module. So based on that, we have N-type PV and we have P-type PV module, and this reflects the base material. P-type is doped. Essentially, PV modules are doped with some certain materials, right? So if it's a P-type PV module, it is doped with boron, while N-type is doped with phosphorus, right? So essentially, the N-type is a better, the N-type has higher efficiency, it has a lower degradation rate. Yeah, so the N-type is kind of superior to the P-type. I just want to put this out. But however, when we're talking about types of PV modules, you cannot classify PV module. We only have three kinds of PV modules, which we are going to come to in the next in a few slides. But this N-type and P-type is essentially how the cells are being manufactured. So another solar energy technology is the solar thermal. So there is a PV module and then there's a solar thermal. Sometimes we confuse this and they are not the same thing. So the solar thermal uses solar energy to generate heat rather than electricity. So the PV module generates electricity, but the solar thermal generates heat. It is important to distinguish between these two different technologies, which are often confused since they both use the same source of energy. So you will have seen in some roof, although they are not very common in Nigeria, but if you move around the city centers or in the cities, sometimes you see some of these solar thermals on buildings on top of buildings where they are used to generate heat or hot water. So this is how it works. Okay, so this is of course, when the sun shines and it hits on any surface, it generates heat. It increases the temperature of that surface, right? Now, from basic science, we know that black surfaces absorb heat more than white or light surfaces. White surfaces actually reflect heat. Black surfaces absorb heat, more. And that's why you will notice that some of these solar thermals are black because they are, it has to absorb the heat from the sunlight to generate hot water. So the water comes in from a tube and it flows, within the panel. And while it is flowing, it is absorbing the heat from the sun. And by the time the water is flowing out, it is warm or it is hot. So that's a different way of generating hot water. Instead of using your electric resistant heater to heat and to heat water and then generate the hot water. So these are the two different technologies side by side. So here is solar PV module, and then on this side you have the solar thermal for generating hot water. So let us look at different configurations of a PV system. We have the off-grid and we have grid connected PV system. There is an off-grid and then there's a PV grid connected system. So let's start from the off-grid PV system. So the off-grid PV system, it has elements like, okay, so you have the sun, which is the primary source of the energy. It goes through the solar panel that actually converts the sun energy into direct current, right? And then this direct current now have to go to a storage. Now it's still at direct current level. So if you have a direct current light bulb, you can actually connect it directly and it will light up the light bulbs. But if you have an AC light bulb, what that means that it has to go through an inverter, right? To convert it from DC to AC. So with this kind of configuration, what we have is an off-grid system because it does not have any connection to the grid. It does not have any link to the grid, okay? So you have a charge controller. So essentially what this charge controller do is to manage the kind of current that goes into this battery, because this battery, if you don't manage it, it will damage this battery. So charge controller is here to manage and regulate the current, okay, that goes into this battery and the voltage that goes into this battery to actually, charge the battery. And then from here, it then goes through your inverter and then it powers your appliances. Then there is the grid connected PV system. So for the grid connected for the grid connected PV system, it's have a slight different configuration. In this case, now you have connection with the grid. Okay, so you're feeding the electricity that's produced from your solar panel, you're feeding it into the grid. It's not very common in Nigeria. However, we have it existing on a large scale, not on a small scale. If you go to places like Germany and some other developed countries, they've made it so that you can actually connect your home solar system to the grid. Okay. Yeah, so for that kind of station, it's grid connected. As long as you have that connection to the grid, it becomes a grid connected system. And this is important because for sometimes when you have a grid connected system, sometimes it also reduces the need for battery storage. So essentially, you're storing your energy on the grid. Okay. So the idea is that while you're producing excess electricity from your solar panel, okay, more than you can use in your home, instead of curtailing it or instead of allowing it to waste, you send it to the grid. Now, at that time during the day, a lot of businesses are up and running and they need power, they need electricity to function. So they actually take that electricity, they take that energy and they use it, okay? And why they're using it, so what actually happens is that the fossil fuel generator or the gas generator that should produce more electricity is now curtailed, is now reduced. Okay, so by reducing it at the generation end, then you're actually reducing the cost of energy, or as well, you're also reducing the impact of climate change by burning those fossil fuel. But again, what happens is that during the night, when you now need the electricity, now remember you did not store enough of it, or you did not store the electricity at all. During the night, when you come home and you need electricity to work, then you can collect back from the grid. Maybe at that time, the fossil fuel generator can now be running. Okay, it will not feed you back. So at the end of the month, you will not do you not compare how much have you given to the grid and how much have you collected from the grid. If you have given more to the grid, then you're entitled to some compensation, either in the form of maybe carbon credit or in the form of financial reward. So depending on the country where this is. So this, what I just described to you now is known as net metering. So for countries where you have a net metering program, this is the way, this is the structure, and this is the arrangement, through which, you get rewarded, by connecting to the grid. Now, there are different ways, or this is just one way of connecting to the grid. At a small scale, at a larger scale, in that case, you can now be, in that case, you're just like a solar generator or like a solar farm. But I don't want to push too much because we're going to get to that. So, stay on the PV and off-grid and then grid-connected PV system. So I just like to break them down. Okay. So for the off-grid system, you have a PV. I mean, now these are just examples. So you have PV system for rural community or rural electrification. Rural electrification means that they're off-grid. Now, you know the kind of mini grids we have in Nigeria, where you have a central solar generator and then you have the grid, that is connecting to the homes. When you have that kind of arrangement, it is still an off-grid system. Okay, in as much as it's a rural mini grid, but it's still an off-grid system. Okay, so this kind of system can have battery, and some of them can come without batteries, right? Some can come with generators as well, because sometimes, because of the intermittency of the sun, sometimes there might not be enough generation, and you might need to use generator, to augment, your storage. So all of this I have described is still an off-grid configuration. There are standalone mini grids, which is essentially what I've discussed, which I've talked about. There are also purely PV systems. I've talked about this as well. Some of these rural mini grids, some of them are pure. I mean, there is no storage, and there is no, okay, there is storage, but there is no generator. Okay, but what happens in this case is that in the case that the sun did not shine enough to generate the amount of energy that is required, then there won't be any there won't be enough supply. So for some part of the day or during the night, they will have supply. But again, you have a hybrid system. So some of these rural mini grids, you might hear concept like a hybrid mini grid. If it's a hybrid, then you have other sources of energy production. So it can be generator, it can be a combination of generator and PV, it can be a combination of generator and wind. Okay? But we are not, the wind system is not very common in Nigeria because of maybe the wind speed that we have in Nigeria might not, be very viable, for wind energy. So we also have the large PV diesel hybrid mini grid for industrial applications. This is typical for some industries. So there's a brewery in Ibadan, I think Nigerian brewery in Ibadan, that has about 600 or 700 kilowatt peak installed solar system. I can't remember exactly the capacity, but the point is like it's a hybrid industrial system where they combine the energy that is coming from the solar system, they combine it with the grid, okay? And they also, so it's a hybrid system, meaning that it has a multiple source of energy supply. So for that, in the case of that industrial complex in Ibadan, they have solar PV system, they have generator, and they also have the grid. Okay, so now let me add that when you have this kind of arrangement or this kind of configuration, in most of the cases, or in most of the time, the solar system cannot function independently. So the solar system needs the grid or it needs the generator to run in most of the cases, right? And the reason is because the solar system is a non-dispatchable source of or non-dispatchable technology or non-dispatchable generation technology, right? What that simply means that you cannot, so during the evening time, you cannot say, okay, you cannot say, okay, you need 500 kilowatt and the solar system gives it to you. No, it's dependent on the sun. So it is non-dispatchable. Now that is different from generator, right? You can add any load at any point in time, as long as you have not exceeded the capacity of that generator, the generator will give it to you. But it's not the same thing for solar system. If you have a 1,000 kilowatt peak of solar system, right, and the sun is not optimal, you cannot demand for 900. It cannot give it to you. So it is not dispatchable. So because it's not dispatchable, in most of this, it cannot function alone. Imagine that you have only the solar system running your industry and the sun drops. What happens? It will cut off, it will shut down, right? And then your industry will not function. But when you have it in combination with the grid, so it is combining the electricity that is coming from the grid and that is coming from the solar system. However, it's going to prioritize the electricity that is coming from the solar system. The electricity that is coming from the solar system will be priority. We take the higher priority of dispatch, right? So it will be dispatched first, and then the remaining one will now come from the grid. So what happens is that when the sun goes down, right, the grid comes up, okay, and then your system can keep running. But again, then what happens if there's a grid failure? Imagine that maybe your demand on the solar system is, for example, 500 kilowatts. Okay, that's your demand. And out of that 500, only 200 is coming from the solar system, meaning that 300 is coming from the grid. What happens if the grid fails? So what will actually happen is that once the grid fails, the solar system will shut down. Okay, but some of these are designed such a way that once the grid fails, the solar system control panel is the solar system controller, not the control panel. The solar system controller will automatically start your generator and then connect you back, to supply. Okay, so all I have just said now is still an off-grid configuration. In as much as you have a connection to the grid, but it is still an off-grid because you're not feeding into the grid. The energy that is generated from the solar panel is not feeding into the grid. In fact, there is no connection to the grid. There is only an interface, okay, where you take supply from the grid and then merge it with what is coming from the solar system. Okay, now that is different when you have a grid connected PV system. So for grid connected PV system, you have distributed PV system feeding electricity, onto the low voltage grid. I have described this, I've explained this already when I talk about your home solar system that is feeding into the grid, you know, during the day when you're not at home. It's feeding the generation into the grid. So that is
Sir,
distributed.
please, I want to ask a simple question. Sir, I want to ask a simple question on this commercial industrial. Are there institutes that run a special program on this PV grid connected this? Because I know what we are more or less doing is general introduction to all this. Hello?
Sorry, I didn't hear that. I think,
hello?
Yeah, please, can you repeat it? Yeah, yeah, I can hear you.
I'm saying from the previous introduction you made, I know in terms of going deep in all this, let's say commercial / industrial PV grid connected system, like the one we have in Federal Ministry of Works, we see that system is more of a hybrid system. It has a diesel, it have a utility, it has solar. It's unfortunate currently I observe it's not working. Is there any institution where you can refer us? We have a training on such
that system is still working.
Other than just general introduction.
That system is still working.
The last time I visited the office, that was last month ago. I was there around 6 p.m. Everywhere was dark.
It could just be a little temporary, maybe
to your surprise,
Let me just explain
it was, I wouldn't like to go deeper because of privacy, but that was my experience really.
So let me just explain it to you. You know, around that 6 p.m., maybe 6 p.m., maybe the interchange or the control system that our lecturer just spoke about now just had a little failure, and it's just a matter of restarting it, and the system will pick up back.
Although weather was cloudy, I must admit to the fact my major introduction, where you can recommend us on running a training on area of this commercial / industrial PV grid connected solar system design and installation.
Okay, thank you, Engineer Emmanuel. I heard you very well. So sometimes the design of this system, sometimes if they are not properly designed, it can also lead to failure. I'm not saying that that's the case for what you have experienced. It could also be that just like your colleague have also said, that it could be from the control system, right? So there could be many reasons why, you know, there might not be supply at some certain time. However, at the design stage of the system, you know, the sensitivity of the load has to be taken into account. So if you have a sensitive load that are connected to such system, because of the that interruption when the grid fail, you need like about 10 seconds to start up the generator and then connect it back. If you have sensitive load, it might become necessary to find a way to make sure that while that transfer is going on, the load is not interrupted. So now coming to your question about maybe trainings and all of, some of these things are simulated, especially if it's whether it's an existing building or existing facility or a new facility. Sometimes the best way to go about them is through simulation. So there is HOMA software that is used to simulate some of these things, right? I think we're going to talk about it. HOMA is basically is a hybrid optimization model. For energy resources, right? So where you have multiple sources, you have solar system, you have grid, and you have generator. Okay. So in the HOMA software, you now tell this HOMA, this is the grid availability, right? Sometimes the way, in fact, to do this correctly, the way we normally do this, achieve a high accuracy in the design. Sometimes what we normally do is that we log that facility so we can see the grid availability, over several months, if not up to a year, but sometimes it's difficult getting up to 1 year data. So we can log for several months. So we see the peak demand on that login, we see the availability of the grid, right? And we see the outages. Okay, and we feed this information to Homa. The Homa now fills those outages with the solar PV system and generators, depending on the one that has the least levelized cost at every point in time, whether in the morning, afternoon, or night, right? But we're going to talk about it, about the Homa software, but we might not have all the time to go into the full design. But if it's something that you're interested, okay, I'm sure there are people that offer a full training program on Homa software. I think that is something that we plan to do anyway. Yeah, but I will we'll communicate to you. I mean, when we are ready to do that, where we're going to focus basically on this hybrid systems, and we run a training on Homa simulations, how it works, because sometimes softwares are garbage in, garbage out. You need to understand what you're feeding in. If you feed in the wrong data, obviously you're going to get.
Can I just educate him a bit, sir?
Okay, come in.
Thank you very much, sir. It's just to Engineer Oji. It is not. It is not.
Excuse me, sir.
Yeah.
I think we should concentrate on the scope of our training.
Oh, okay. Yeah, I agree. I agree with
you. Can have your own private session.
Yeah, no problem.
Okay, okay.
I agree with you.
Absolutely. Okay. Okay. All right. Thank you for that. I think you know yourself. You can actually discuss this and at your own time. So now we are talking about the grid connected PV system, and I was trying to explain how it works. Especially if it's a hybrid system. A lot of times, if it's an industrial settings, it's usually a hybrid system. But you also have a central PV system that is feeding electricity into the medium or high voltage grid. In that case, you have a large scale PV power plant. So in that case, it's not a hybrid system. And a typical example is what we have in. I think we have some examples of this large scale PV system connected to the grid. I know very well of the one in Kano because I was largely involved. In the one we have 10 megawatts solar power plants. Somewhere around Kumboso. There's an industrial cluster in Kano. So the idea was to support the energy need with solar systems. So there was a 10 megawatt, and toward the end of Buhari government, he commissioned that project. Okay, I've not been there to confirm or to see how it is working, but I know I was largely involved, in the design stage and the feasibilities. So that is a typical example of a grid-connected PV system. Okay. So when I talked about grid-connected PV system, I talked about the home the one at the low voltage, and this is just an illustration of a distributed PV system. And I think I've explained this. I don't need to waste more time on this so that we can be able to cover up all that we need to talk about today. I've explained how your home can have solar system that is connected to the grid. And I told her that it is called net metering, where you have a meter that reads in both directions. It can send from your solar PV system to the grid, and it can also collect from the grid back to your home. So it's a two-way metering system, and it's called net metering. So it's available in some countries. I know Kenya recently, they have drafted their own regulation on net metering. It's available in India. It's something that is already very common in Germany and some other developed countries. So, and then this is an example of a central PV system. I've already explained this, and I give a typical example of what we have in Kano State. So I'll just proceed. So for an off-grid system, this is just a schematic view of an of a grid-connected system. So you have the PV modules, you have the inverter. In this case, you don't need charge controller. So you have the inverter that just converts from DC current to an AC current. Then you have the meter that measures the amount of energy that you're actually sending out to the grid. And then you have a protection fuse, and then you feed it into the grid. There are some other technicalities, around this. So some of the technicalities also include, the frequency, because you have to synchronize it with the grid frequency. You also have to synchronize it with the grid voltage before you can combine it to the grid. So these are just some of the technicalities that are also involved, but they are not visible, right? Yeah, but just for us to have in mind that before you can synchronize two sources of supply, they must be working at the same frequency and they must be working at the same voltage before you can synchronize them. So this is another illustration of an off-grid system. I think I will just skip this. I've extensively talked about this. Now, this is an off-grid mini grid. It is better to, instead of doing grid extension, because you don't have so much load, you don't have so much consumption at that end, and it's not cost viable. Remember when Engineer Uche taught us about the economic analysis of an investment? When you do a grid extension, the cost of extending the grid to those communities is not worth it because their consumptions are just so little. TV, radio, light, and just, so it does not worth it. So the government, in their wisdom, thought that, okay, why not connect this, isolate these communities and then, electrify them using a mini grid system. And that's how we landed into this whole concept of a rural mini grid. So this is just the concept. And I told us that some of them are, in fact, many of them are, in fact, most, if not all, are hybrid system. I know at a point they made it a standard that if you have a mini grid, it must have a generator. Okay, and the reason is because they want to make sure that at least there is always electricity in those communities. Okay. Dispatchable. You can call upon it at any time and it will give you the electricity. You cannot do that for the solar system. So I think at a point they made it, the government made it a standard for your mini grid to be approved. You must have a generator that is attached to it. And of course, this is a battery system for nighttime use. So let us just move forward to the components of a PV system. Now there are three types of PV cells. N-type and P-type is not a type of PV cell, please. Let's not get this confused. There are basically three types of PV cells, okay? Now, these are selected based on their technical characteristics of silicon base and thin film. So we have monocrystalline silicon-based PV system. We have the polycrystalline silicon-based PV system, and then we have the thin film PV system, PV module, not system, sorry. We have the thin film PV cells or modules. Now, when you combine the cells, it actually gives you the module. So sometimes when I say cells and module, just so you understand what I mean, the cells are just the units of the PV. So the PV module has a lot of PV cells that are now, embellished or embedded on the panel to give you that PV module that will now know as PV module today. So now, what is the difference between these three PV systems? Okay, you have the polycrystalline, you have the monocrystalline, and you have the thin film. The thin film is not very common in Nigeria, but yes, I've seen, sites where it is being used in Nigeria. I'll just, brush over the major differences. Now, for the polycrystalline, it has a lower efficiency. The polycrystalline PV module, it has a lower efficiency. It's relatively cheaper, or it costs less than the monocrystalline, because the monocrystalline has a higher efficiency. And how you will identify this monocrystalline is, I don't know if I can zoom this. Okay, so you notice that at the edge of the square, at the edge of the sorry, is this zoomed from your end as well?
Yes, sir.
Yes. Yes.
Okay.
Yes.
Okay. I just want to know if it's also across or just on my screen. So you can see that at the end of the square, it's at the edge of it. It's kind of cut, at the end of it, right? Unlike the polycrystalline, it's just a fully blocked out square, right? But for the monocrystalline, you will see that it is cut at the end of. So when you see them, you just know it is a monocrystalline. And for most of them, most of the monocrystalline, they're darker in color than the polycrystalline, most times. Okay, so you can identify when you use monocrystalline and then the polycrystalline. Then the thin film is, sorry, is anyone asking a question?
No, sorry, no.
Okay. The thin film solar panels are dark. However, they have a better application in areas where you have high weather temperature. They have high tolerance for high weather temperature. So as we proceed on this course, you will see how weather temperature affects the output of PV modules. When you have a high weather temperature, it reduces the output from your PV module. We're going to go into that. We're going to see that, as we proceed in this course. So, but before we get to that point, just so you understand that one of the advantage of this thin film module is that they have high tolerance for high temperature, right? Whereas polycrystalline and monocrystalline has a lesser tolerance for high temperature. So once the temperature of the environment is high, it reduces the output. Yeah. So those are the different. And then between the polycrystalline and the monocrystalline is higher in efficiency. The efficiency of the monocrystalline is high. Okay. Yeah, but and of course now the cost competitiveness between the monocrystalline and the polycrystalline is, the cost competitiveness is becoming more competitive, and then the monocrystalline is dominating the market. Before now, the polycrystalline dominated the market, and the reason is because if you look at the efficiency gain because of buying a monocrystalline and the cost difference, you find out that the efficiency gain is not worth the extra cost. So in that case, you just go for the polycrystalline, But now, because of the cost competitiveness that is, is becoming, stiff, you have more of monocrystalline, and their efficiency has also been improved a lot across both polycrystalline and monocrystalline. But as the market stands today, if you look at the cost difference and the efficiency gain, in most cases, you want to go for the monocrystalline. So I talked about PV cells, I talked about PV module, and then PV array. So PV cells are just the cells. When you look at your panel, your module, your PV module, you will see that it's a combination of cells. Some of them is 60, 72, depending if it is a half cut, but we're going to come to that. Depending on the structure and the arrangement of the cells, you can have more, you can have less. So it depends, but a combination of the cells is what we actually know as PV module. And then when you have a combination of the module, we have what we call the PV array. So the modules are formed by connecting PV cells in series or in parallel and encasing them in a protective material. PV modules can be connected in series, and they can also be connected in parallel in order to form a PV array. The number of modules determine the maximum power generation capacity of the PV plant. Now, I talked about half cuts, and why do we have half cuts? When you also go to the market, I'm bringing out this concept so that when you go to the market and you begin to see some of these terminologies, you can actually understand what they mean, and and you'll be able to advise on which is a better option, depending on the financial disposition or the financial outlay of your clients, or whoever is financing the project, right? So remember when I talked about polycrystalline and monocrystalline, and I told you that monocrystalline, at the edge of it, there's a cut at the end of the squares, right? Whereas polycrystalline, you don't have that. So it's one of the ways to identify monocrystalline and polycrystalline. They will also have a half cut. So half cut is that the cell is divided into two. It's cut into two. And part of the reason is because, remember that as current travels through the cable, now from conventional electricity system, as current travels through the cable, okay, there is a voltage drop, okay, as it moves, and and apart from the voltage drop, the losses also increase, right? So now the idea and the reason behind this half cut is also to reduce those losses. When the current moves from, of course, the current is generated, within the cells, right? But of course, it has to travel and then meet at a point before it flows into your cable. Now the idea of half cut is to reduce that travel length so that you also reduce, the losses, right? And by doing this, you will now improve the efficiency of the module of the cell. Okay, so that's the concept of the half cut. Now, when you put this all together in a model, I mean, you put the cells in a model, you even gain, you gain more in efficiency, right? Because of some certain conditions. When you have a PV system that is not half cut, so this one now is not half cut, right? And imagine there is a shading on one of the cell. If there's a shading on one of the cell, right? Now this shading is actually going to reduce output of this, entire model, right? It's going to reduce output. Essentially, because of the way these PV models are structured, there's what we call a bypass diode, at the end of, at the end of every arrangement, right? So it typically have a 3 bypass diode. So when there is a shading on one of these cells, it will reduce the entire output from this arrangement, okay? And then you have a much higher reduction in your energy output. But imagine when you have this kind of arrangement, you have a half cut, and this half cut is also further divided into 2, in the model, right? So if there's a shading on one of the panels, it's only going to affect a fewer number of the cell, as opposed to when you have, the conventional model that is not half cut. Okay. Aside the fact that you improve the efficiency by reducing the travel length of the current between the cells, you also achieve an improvement in the eventuality there is a shading on any part of the cell. Okay, so these are all what is making the half-cut cell more, making market dominant or having more market, request, right? And again, for the half-cut, you can also embed more cells compared to this. And so when you embed more cells, you can see that you then have a higher output of electricity. So look at this full conventional PV model. What you have here is 60 cell, right? But in the case of the half cut, you have, of course, is when you divide this 120 by half, you still come back to 60, but somehow you have a higher efficiency and a higher output, from the half cut. So now we've talked about the PV model. I don't know if you have any question on the PV model, or do we understand it? Do we have any question around the PV model? Like when you go to the market, or if you want to make PV model recommendation, are there technicalities that you're still not clear about? Because the purpose for me is that at the end of it, you can confidently go to the market and make the best choice of the PV model that you want.
So I have a little question.
Okay.
And it goes on number of cells to determine the wattage of a model. How do you, without using multimeter, looking at it, without using the nameplate of the model, looking at it, expecting the body structure of the model itself, calculate actually what is the wattage of a typical of a model you want to select in the market?
Thank you for the question, because sometimes when you go out in the market, there's a lot of things that happens out there in the market. Someone can easily get a PV model that is 300 watts, for example. All the person needs to do is to pull out the sticker and then put 400 watts, right? So in that case, how do you actually, verify that the PV model that you're buying, is actually the rated output, right? I think that's kind of explain your question, right?
Yes.
Okay. So
I also have a question.
Okay.
Regarding the panels. Now, it's just one of those observations that I've noticed, and I did ask that question when I was in South Africa. If you have panels on the roof and you stand afar, you will notice that you have some, bluish kind of color appearing, in the middle of the panels. It may not be on one point. It could be 2-3 points on a panel. why others do not have. Now, because, during a solar training that I attended in South Africa, I brought up that question, and I think they talked about the quality. Can you please speak to that? Because I have seen the panels that was brought from Germany and also
Thank
Poland.
you.
For more than 10 years, nothing like that appeared on those, panels. But now these days in Nigeria, what we have, for instance, like the one that I used, within 3-4 months, I noticed that color was coming up.
Okay. Okay. Thank you. So let me start with the second question. Hello.
Hello. Is it time for questions, or maybe you just answer these two and then questions again will follow?
Yeah. Let me respond to this too. Okay. Yeah. So some of these things depend on the manufacturer of the PV module, right? We have different manufacturers, and that's why when you go out, some people might recommend maybe a particular PV module or a particular brand over the other. Now, the color that you're talking about that appear could be as a result of several factors, right? So it could be from the production of the PV module, the material that is used in producing the cell, right? Maybe they are reacting to sun. I cannot say that that's exactly is the issue, but it could also be a factor. Right? Like you also you mentioned that you look at the panel that are produced or imported from Germany, and you've not seen those kind of effects. And then you look at some of the PV modules that we have in the Nigerian market, and then you install them, and within some time you already begin to see those kind of effects on them, right? Now, what is left, what is unknown is if maybe there has been some analysis to see if that effect that you're seeing, if it has actually impacted the energy production of the PV module. And that is why it is important that sometimes when we have these PV systems, you have a kind of a monitoring system. The PV module that I have in my house, I can monitor it from anywhere. At every point, I can see what it is producing, and I'm able, because of this, I'm able to track its yield, and I'm also able to see its performance ratio, right? So sometimes some of these things you're talking about can be mitigated or can be understood, looking at existing projects and then see how some of these things affect their energy production. So based on what you said now, I cannot say if that effect has actually affected its energy production. Okay, but again, there are grades of solar panel. Okay, so of course, if you get the top tier, the top tier solar brands, I don't think you might have any issue with the output. In terms of the degradation, because what you just said now, what it tells me is that maybe because after you've installed the solar panel and you use it for some time, okay, if that effect has actually reduced its energy, then which means it's degrading faster than it should, right? So I'm just trying to touch on some of the things that could be responsible for that, but without having this kind of investigation or looking at it, I may not be able to tell you exactly why this is happening. But I think it's essentially from the production process, maybe the production material and maybe the doping. How these cells were produced. Okay. Now coming to the second question on the number of cells, right? Sometimes there are some basic tests, that we also do, to kind of verify, the ratings of these PV modules. Okay, using basic multimeter, looking at the voltage, putting that in the sun, looking at the voltage, and maybe seeing what actually this PV module. But beyond that, you can actually look at the cell and count the cells, right? In the labels, if it's I don't have the exact value of what every cell should be, right, or what the cell should be. Okay, if I have that value, then what you can do is just take that value, look at the number of cells that you have there, and then multiply it, and then you have what the rating should be. Okay, somebody is asking the monitoring device that I use. So the inverter that I use in my own system has that device. All I need to do is to connect it to the internet, and it gives me all of that. Information. I'm responding to a question in the comment section about the monitoring device.
Sir, a little bit stressing. Is there any way monocrystalline and polycrystalline material can be joined to produce a single module? Because I saw that in the market, I saw similar thing in the market. Some area is blue, some area are black. They still be disposed to for sale.
So if you combine both of them, what you have essentially done is that you're reducing the output from, depending on the configuration, how you're able. So it's possible to do that, but what's the configuration? Are they connected in series? Are they connected in parallel? Are they connected to a central inverter? Are they connected to a string inverter? So it all depends. We are going to talk about some of these configurations. As you
thank you, sir.
Training, there are different configurations. So it all depends on how. If you connected the two of them, such a way that what you have essentially done is that you have reduced the output from the higher efficiency panel to that of the lower efficiency panel. That's what that's what you've done essentially, right? If you're connecting both of them in series. Someone is asking, why is the mono panel more expensive than the poly panel? Of course, because of the efficiency and the production technology. The efficiency of the mono panels is higher. It has a higher efficiency, and with that higher efficiency, you're not expecting to go at the same price with what comes with at a lower efficiency.
Yeah, of course.
Okay. So let's talk about inverters. So inverter, remember when I said that PV modules actually produces, they produce DC currents. So you need an inverter to convert it to an AC current. So an inverter converts direct current input from a PV array or battery into an alternating current. Okay, so you have the sun that is coming, from the sky above, and it hits your PV module. It generates a DC current. You need an inverter to convert it, to an AC current, and you can feed into the grid, or you can use for your home. So essentially, that's the role of an inverter in a PV system. So we have different types of inverter. Okay, there are basically 3 types of inverter. So you have the micro inverter, which are directly connected to the PV module. So micro inverters, it's actually somehow it is good. It helps you to improve the efficiency of your PV panel, especially when you have shadings, because in this case, every inverter has, every PV module has a micro inverter. So as soon as it's producing the DC current, at the module level, at the PV module level, it is converted to an AC current. But of course, it comes at a higher cost. So sometimes when you look at the cost, it might not make economic sense. Okay? But there are such kind of inverters. Then we have a string inverter. String inverter, which are connected to one or few strings of PV modules. Each string can have up to 20 PV modules. So it depends. So now that comes back to the question that someone asked about combining mono and poly. So it all depends. If you have in the same system, you have mono that is connected in one string, and then you have the poly that is connected in one string, there's not a problem about that, right? But however, the poly we do less at the same irradiation. The poly module or the string from the poly system we produce lesser electricity than the string of the mono, right? So this is a string inverter, and then we have a central inverter. So a central inverter is which are used in a large PV pack of several megawatts, because many strings can be connected to the inverter. So you have, instead of having a string inverter, you are now moving all the whole string into a central inverter. Okay, it has its own cost advantage. It also has its own maintenance an operational disadvantage as well. Okay, so it all depends on the size and scale and the purpose of your design, right? But in most cases, string inverters are more ideal, where you have several number of panels connected to one inverter. You have another several number of panels connected to one inverter. So that's about inverter. Okay, now let's talk about mounting structures. So the fundamental requirement of mounting structures are that they must support the weight of the PV module, and they must also distribute the load evenly onto the roof or the ground below, and they must withstand expected extra loading. Example is maybe rainfall or wind or snow, depending on the climate where this is being installed.
Hello, sir. Hello, sir.
Yes, sir.
I have a simple question before you go. And that
okay,
question inverters. I understand there are for you to charge your battery and be able to make sure it doesn't overcharge or undercharge, you need what's it called? Charge controller.
Yes.
I also know that there are inverters they call hybrid inverters that have their own MPPT things attached to them. Can you please explain?
Yes.
Please differentiate between them.
Okay. Yes, I think I will come to that when we talk about the I will talk about, because when you say MPPT, I mean, what is MPPT actually, right? We need to talk about that. They will not understand how it is being attached to some inverters, right? So charge controller essentially is what regulates the amount of current that goes into your battery, or rather the amount of voltage that goes into your battery. Okay, we're going to talk about it, but let me just give you, because you've asked, let me just give you a brief explanation why that is happening. Now, your battery has a standard voltage, or your system also have a standard voltage, so, but let me bring it down to battery level. Some batteries are 12 volts, some are 24 volts. Now, your solar PV system does not have a consistent voltage, right? Depending on the sun, right? It does not have that, consistent voltage, but your battery needs a certain voltage to work. And again, sometimes your solar PV system can produce a higher voltage. The rating of your solar PV system can come in at a higher voltage. If you allow that higher voltage to go into the battery, it's going to damage the battery. So what the charge controller does is that it converts the current, the voltage to current, and regulate the voltage that goes into that battery. So if your battery is rated 12 volt, it makes sure that only 12 volt gets into that battery. If you have excess voltage, it converts it to current. Okay, so that's why you have charge controller in the first place. Now, some inverters have inbuilt charge controller. Right now, if an inverter has an inbuilt charge controller, care must be taken to look at the rated input of solar module that can go into it. If you exceed the amount of solar panel that should go into it, you can cause damage to that inverter. So, and that is the disadvantage of an inbuilt of the hybrid inverter, right? There's a limit to the amount of solar panel you can connect to it. Okay, but we're going to come to that.
Thank you, sir.
Let us remain on the mounting structure. We're going to come to that. So the mounting structure should have an optimum orientation and tilt angle to maximize power output, and all shading should be avoided. Now, the structure will typically be made from aluminum or galvanized steel. Painted steel or wood are also options, though such structures will probably require more maintenance over the 20+ lifetime of the system. Now, when you're choosing mounting structures, of course, most of the mounting structures are galvanized steel, right? And the reason is because these solar panels you're mounting is expected to last for more than 20 years. Now, if you use wood can easily degrade because of the exposure to the climate exposure, right? It can easily degrade before that 20 years. And what are you going to do? Do you have to now go and remove them and then so it does not actually make economic sense to use wood as a mounting structure. Okay, so it's ideal to use a galvanized steel that can last, the lifetime of the solar system. So there are different types of mounting structures. solar panels can be installed on a fixed support or on a tracker. Tracker is hardly seen in Nigeria because of the cost,
Hello, Engineer,
cost.
Engineer Chima.
Yes, sir.
You told us that tilt angle is important.
Yes.
What is an optimal tilt angle and direction for Nigeria?
We will come to that, please.
Okay.
Yes, we will come to that.
Okay, thank you.
We will come to that, yeah. So now we're just on multi-structures and on. So we have a fixed support and we have a tracker. And the reason why you don't see tracker, a lot in Nigeria, because tracker is a mechanical device. And when you have a mechanical device, it requires more maintenance. And you have to factor in the cost of that maintenance and the cost of that tracker itself. When you look at the extra energy that you're going to get from using a tracker and the cost, it wouldn't make economic sense. And that's the reason why you're not seeing so much of a tracker system, in Nigeria. I mean, it's used in some places around the world, but when you, like I said, if you look at the cost benefit analysis, it may not make that economic sense. So, and that's why we fall back to the fixed support that is most often used, in Nigeria. And I want to believe that we understand what a tracker is. A tracker are motorized structure that follows the path of the sun. You know that the sun rises in the east and sets in the west, right? So if you have a tracker, it actually follows the sun. As the sun moves, it follows the sun to make sure that you have an optimum, yield from your solar panel. So trackers are motorized structures. I think I've already explained this. You have a single axis tracker and you also have a two axis tracker. So a single axis means it can move from east to west, while you have a two axis means it can move from east to west and as well as north to south. Okay, so depending on what, it can actually adjust itself to be sure that it's at perpendicular with the sun to get an optimum yield from that sun. So let us look at the physical aspect of a PV system. Now we're coming back to the PV system because it's at the foundation of the PV module. So the electrical power P for DC system measured in watts. We already know that in our first introduction, we talked about power, and I know we learned about this formula where we said that power is equal to voltage times current, and of course times power factor if you're now considering the load. Okay, so power is equal to voltage times current, whether it is direct current or alternating current, it's the same, right? So that's how power is measured. So the power is a product of voltage and current. Now, how does this work on the PV level? Now, under normal sunlight condition, PV cells voltage remains fairly constant. However, the cell's current is very sensitive to sunlight. Higher solar irradiation will produce a higher electrical current. Low solar irradiation will produce a low electrical current. So what this simply is saying that once the sun comes out, the voltage of your PV module is relatively constant. It does not change so much. As long as the sun comes out, it does not change so much. But what actually changes so much is your current. Remember that power is a product of voltage and current. So when the sun comes out, the voltage is almost, relatively stable, but this current changes so much. If the sun increases, the current increases. If the sun reduces, the current reduces. And when you put this as a product, it ultimately affects the power that you're getting from the PV module. So one of the things that increases the yield of your PV is the intensity of the sun. Once the intensity of the sun increases, your PV module output increases. So that is one thing that we should note. Another thing that also increases your output from your PV module is the surface area. Okay, so the surface area of the PV cells also affect the electric current. A cell with a larger surface area will produce more electric current than a cell with a smaller surface area. So if you have a PV module that is or a PV array that has a bigger area, it is expected that you generate more electricity. Thus, the two main factors that affect the output of a PV cell are the intensity of the sunlight falling on it and the size of the cell. Other factors are also important and will be discussed in the following section. Now, let us dive in a little bit into the technicalities of how PV cells, how they work. So this is an electrical characteristic of a PV cell, and we call this IV curve. IV curve, that is current voltage curve, right? And from here, we're going to derive that concept of MPP, okay? The MPP that one of our colleagues talked about. And from here, we can now, talk about that concept of, some inverters having hybrid and all that, okay? So let's talk about the IV curve. So please, I want you to look at this diagram, okay? The diagram that is here, okay? So this diagram describes an important electrical characteristics of a PV cell. At any given time, a PV cell is operating with a specific current and voltage, which lies along the IV curve. Now, this is the IV curve. The red line is IV curve. This red line is IV curve, right? Now, this line shows the current. Current is I. Take note of that. The current is I. Now, this line shows the current which is produced over a range of voltage. And this current is known as ISC. And this is ISC means short circuit. Short circuit. And short circuit current is the value at which the current is at maximum and the voltage is equal to 0. Now, I want us to look at this formula. If this current, assuming that the sun is having its highest intensity, right? And the current is maximum, right? And this voltage is 0, what becomes the power? I just want
zero.
Okay, so this power becomes 0, right? Now, and when this happens, we know it is known as an ISC. That is at the point of where the current is maximum and the voltage is 0. Now, let us look at this diagram. This vertical axis is the current. The vertical axis is the current. Now, the horizontal axis is the voltage. Okay. Now, when this current is maximum, now the current is maximum. This is the current here is maximum, right? The voltage is what? 0. Okay, so at this point, your power is 0, right? Now, let us reverse this case. If your voltage is maximum, now your voltage is maximum, right? And your current is 0. What becomes your power? 0 as well. Okay, so now that presents a case. So at what point in this IV curve can we have a combination of the voltage and the current that will give us the maximum power? That will give us the maximum power, right? Now, let us remain with this red line. This red line is IV curve, right? Now, remember when I said that if we stay here at this point, this is the maximum current, but the voltage will be 0, right? Now, if we travel along this red line, okay, and we come down to this place, now this point is where you have the maximum voltage, but the current is 0. So, like I said, we have to look for a place along this line where a product of the voltage and the current will give us the maximum power. If you begin to increase from here, okay, your voltage will still remain, high, right? But your current will be low, and then you will not have the maximum power. Okay, I don't know if this is making some sense. First of all, do we understand the problem that we are trying to solve here by trying to find somewhere along the IV curve where we're going to get the maximum voltage and the maximum, where we're going to get a maximum power, from the voltage and the current. Okay, let me just continue. Maybe when I read this, because there are some other times I also need to define. I've talked about the short circuit current. Okay. Now, short circuit current is at the point where the current is maximum, but the voltage is 0. Okay. Now, I also need to talk about the concept of an open circuit voltage. Open circuit voltage. Now, open circuit voltage is where the voltage is maximum, but the current is 0. Okay, that is open circuit voltage, meaning that the circuit is open, the voltage is maximum, there is no current that is flowing through it. Okay. Now, the power curve of the PV cell is shown by the blue line. This is the power curve, right? So this line shows the electric power produced over a range of voltages. Under normal operating conditions, the curves grow and contract along both the current and the voltage axis. Now, this is where the concept of MPP is derived. Now, MPP is the point at which the cell produces the maximum power. And this occurs at the knee of the power curve where the product of voltage and current are greatest. And that is the maximum power. Now, let me explain this. Now, this is the voltage current line, right? Now, from what we have explained so far, this is the point where you can achieve both, the product of the voltage and the current is going to give us the maximum power. Now, let us move a little bit from this and see what happens. Now, if we begin to move this from here, if we begin to move up, what happens? If we begin to move up from here now, what happens? The voltage will begin to reduce, and the current will increase slightly. Now, if we are moving up, right? Now, this is the voltage. If we move up, meaning we are going back. So the voltage will reduce slightly, right? And then the current will also reduce. So meaning that this power will begin to reduce because the voltage will reduce, the current will reduce. No, the current would increase, but it will increase slightly. But you do that, you're not going to, this power will begin to drop. If you decide to move down, if you decide to move this point down, right, the current will reduce. Now, this is the current. Now you're moving down, the current will reduce, but the voltage will increase a little bit. Now, when that happens, it's also going to reduce this power. So this is the point where the combination of the voltage and the combination of the current gives us the maximum power. And at this point, this is the point where it is known as IMPP, that is maximum power current. Maximum power point current. That is, this point is where we have the maximum power point current. And at this point also, we have the VMPP, maximum power point voltage. This voltage could have increased to this point, but the moment you try to increase it, you reduce your power and then you reduce your current and then the power will drop, right? But this is the point where it is, you can get the maximum power at this voltage. And this is where we derive the concept of MPP, maximum power point. Okay? So now, when you see an inverter that has, or charge controller rather, you know, of course, some inverters now have inbuilt charge controller, in which case it's called a hybrid inverter. So when you see a charge controller that is an MPPT charge controller, right? What that simply means that it can automatically regulate, you know, this voltage and current to give it the maximum power. That is the meaning of the MPP or MPPT charge controllers. It can automatically find. Yes, sir.
Thank you very much. I have been wondering for a long time, what is the effect of MPP? Of what value is it? What does it do for me? So now I know that the charger or the inverter can automatically adjust voltage and current for me to get MPP.
Exactly, to give it the maximum power. Okay, thank you for that. So that is the reason why you have the MPP. Okay, you have, you know, other type of charge controller, right? Pulse width modulation charge controller, right? But this is the dominant in the market, right?
Okay, good.
Okay, so now the maximum power point is equal to the maximum power point of the voltage times the maximum power point of the current. That gives you the maximum power point.
Oh.
That is of the output of the panel. So let us look at factors affecting the power output of a PV system. What are the factors that affect the power output of a PV system? So electrical characteristics of the IV curve is what we're going to look at. So there are three critical factors which affect the instantaneous output of a PV cell. There are three factors. Now, one of the factors is the solar irradiation, or the incident, or the solar incidence on the surface. I think we've explained this. If the solar incidence on the surface increases, then the output also increases. One of the things, another thing that could affect is the temperature. I think I mentioned, I talked about this when I was talking about the type of PV models, and I told her that the thin film PV model is has higher tolerance for temperatures. So when the temperature increases, right, on the PV model, when the temperature increases on the surface of the PV model, it reduces the output. So temperature has an effect on the PV model. And then the next one is the electrical load resistance connected to the PV cells. Okay, so let's look at some of this in detail. Now let us look at the impact of irradiance. Now remember when I told her that once the sun comes out, the voltage remains almost constant. I mean, it does not change so much. Once the sun comes out, irrespective of the intensity of the sun, as long as the sun comes out, the voltage is relatively steady. Now, this graph helps us to understand that. Now, remember the IV curve. This is the voltage, and this is the current, right? Now, in the morning, once the sun comes out, once the sun comes out, this is the voltage can be highest at this point. Once the sun is out, right? The voltage can be highest. But once the sun begins to hit the surface temperature of the panel, the voltage begins to reduce. Okay, you can see that this is the highest point of the day when the sun is, the intensity of the sun is highest, and you can see the impact on the voltage. Okay, the voltage is actually lowest, right, at this point. So now let's look at this value that I give you. This is just the sun irradiations, right? So in the morning, when the sun is just around 200 watts per meter square, right? Around 200 watts per meter square, you can see. Let's see. Okay, now this is the current. The vertical line is the current, and the horizontal line is the voltage. Like I said, right? Now, once the sun begins to increase, you can see how the current, increase from 200 to 1,000 meters square, and see how the voltage has also performed. Let me see. Okay, see how the voltage has performed. The voltage increased a little bit as the sun is coming out, right? There are two things I want us to know. Once the sun comes out and the sun begins to increase, the voltage will increase slightly. But the temperature, once the temperature, okay, let me not confuse us. When I get to the temperature, I'll talk about it, but now let's not remain with the irradiance, not the temperature of the sun. Let us remain with the irradiance. So once the irradiance increases, the voltage will also increase, but it will not increase significantly. Okay. This is 200 watts per meter square. This is the current, and this is the voltage.
Excuse me.
By the time this 200 gets to 1,000, look at where the current has gone, but look at where the voltage has gone. It's the movement of the voltage is. Yes, I can hear you, please.
Yeah, I'm asking, can you make it a little bit wider? Do the zoom in so that I could see the cursor properly.
Okay, sorry.
Not on the page. Okay. Yeah, that's all right. That's okay. Thank you.
Okay, all right. So this is what I was saying. In the morning, when the sun comes out at 200 watt per meter square, this is where the current is. This is where the voltage is, right? Now, when this 200 gets to 1000, the current will have moved significantly, but the voltage will have moved just marginally, just slightly, right? Now, that is the impact of irradiance. The irradiance does not so much affect the voltage. It has so much impact on the current. And once the current increases, of course, the output of the panel will then increase, right? Now let's move to the next. So I think I've already explained some of this literature that I have here. Of course, this slide will be shared with you, and you can read it, and then combine that with the videos and what I've said here. You get the whole picture of the knowledges. Now let us look at the impact of temperature. Before it was a little bit when I was trying to mix up both temperature and irradiance, but then I think I needed to separate them, right? Now, this is the impact of the temperature, okay? Now, in the morning, when you have a lower temperature, the temperature is 25, right? The temperature is 25. Now, look at where the voltage is. The voltage is good. It's high. It has a very high voltage, right? And then look at the current. The current is also high, right? I mean, at this temperature, let's assume that the sun is already fully out, but the temperature has not increased, right? So in that case, the current is high, but once the temperature of the module begins to increase, now this is 25, this is 50, this is 75, right? You can see that the voltage begins to reduce, right? The voltage begins to reduce. Sorry, this is minus 25 because this is minus 25, this is 25. So here it's 0. So once the temperature is 0, they have an optimal voltage. But when the temperature is even minus, it improves the voltage. Okay, but this is, this is hardly occur when you have this minus temperature, except maybe in places like maybe in Germany or somewhere in Europe, where the weather can be so cold and yet the sun is out, okay? Then you can have maybe minus, but I don't think it gets to minus 25. But the point is that once the temperature begins to increase, the voltage begins to drop, and it drops significantly, right? Compare with the current. You can see with the current really moved, okay? From 0 degrees centigrade to when the sun was at 75 degrees centigrade, the current did not move as much, but you can see how much the voltage has moved, right? So now let me tell you this from practical experience. During the rainy seasons, right? When the sun is fully out, you will notice that the weather temperatures are not always high. At that point, you always have the highest yield from your solar panel. I mean, during the rainy season, when the temperatures are not so high and the sun is fully out, at that point, you usually have the highest, yield from your solar panel. If you have been very observant and monitoring your solar system, you have noticed what I'm telling you now. And then during the harmattan, during the dry season, during the hot weather, even when the sun is at optimum, it's very high, and the weather is high. The intensity is high, but that intensity also comes with a higher temperature. So that higher temperature will reduce the output for your module. Okay, so you will not have the same yield as you will have had during the cold, rainy weather period. Okay, I'm just saying this just so you can understand the impact of temperature on the yield of solar panels. So this is how temperature impacts or affects the yield of your solar panel. Now let us look at standard test conditions. Okay, when you go to the market, and this also has to come to the question that one of our colleagues asked, where you said if you go to the market, you see a solar panel that is rated 300 watts. Why is it rated 300 watts? Okay, so there's what we call standard test conditions, and these standard test conditions are the conditions upon which these modules are given their ratings. Okay, now there are about 3 items that we're going to talk about. So due to the variability of power output of PV cells, depending on parameters such as irradiation, temperature, that we talked about this already, and the performance of different cells operating under different conditions, they cannot be compared easily. If you have a certain solar panel installed in Germany and you have another panel installed in Nigeria, you might not be able to compare them because their operating conditions vary. The temperature, the irradiance, they are all different. So you might not be able to compare them, So if that is the case, then at what condition is the solar panel, at what condition are they giving their ratings? So in order to enable meaningful comparison between PV cells or PV modules, the rated output of the cells or modules is always measured under specific conditions. So these conditions are standardized across all testing facilities across the world and are called standard test conditions. Now, there are about 3 items. One of them is the light spectrum, or the AM. The AM is like air mass or light spectrum, is 1.5. And then you have the irradiance. So the solar panels are tested at 1,000 watts per meter square. That is the standard test condition before they can be said, okay, this is 300 watt solar panel. And there's also a temperature. They are tested under 25 degrees centigrade. Now, if a solar panel is rated 300 watts, for example, and you take it and you install it, and then that solar panel is operating below 25 degrees centigrade at 1,000 watts per meter square, trust me, that solar panel is going to produce more than 300 watts. It is rated 300 watts. But because of the gain in the lower temperature, remember I told us that temperature affects the output. A lower temperature will increase the output. So the panel was tested at 25 degrees centigrade. So what that means that if you have a higher temperature, higher than 25 degrees centigrade, you will not achieve that 300 watts. That's what it simply means. So if a panel is rated 300 watts, for you to mount that solar panel and achieve 300 watts output from that solar panel, then that solar panel has to be operating at a 25 degrees centigrade, and it also has to be, the solar irradiation at that point has to be 1,000 watts per meter square. And it also has to be at a light spectrum of 1.5. So these are the standard test conditions. So each finished PV module or PV cell leaving the production line undergoes a flash test. It is exposed to a flash of light under careful control of the standard test conditions parameter, lasting only milliseconds. It's not even up to 1 minute, 1 second, milliseconds. And then the output performance is recorded. This output performance is what is now labeled as maybe 300 watts, 400 watts, 500 watts, or whatever the case may be. So subsequently, the cells or modules are sorted and sold according to their rated power. The rated power is measured in units of watts peak. That's why you say solar panels. You say, okay, the storage of a solar panel is maybe 200 watts or kilowatt peak. Okay, because that's the peak it can actually produce, at standard test condition, or kilowatt peak, and refers to the rated power under standard test condition. So let's just quickly move. Now, temperature coefficient. Now, this temperature coefficient is trying to make us understand how increase in temperature how it affects the output of your module. Okay, so when you look at some of the, if you look at the technical details of some of the modules, sorry, I'm just trying to see if Engineer Samuel Ojo, you raised your hand. You want to ask a question?
My question, when you were explaining the effect of temperature on the solar, on the output of the module, I couldn't get you very well. I was distracted that time. So please, if you can just repeat that area.
Sorry, you say what I was talking about, the temperature or what?
Yes, the effect of temperature on the solar panel.
Okay. That's, I mean, we are still on it. We are still talking about temperature coefficient, and what that simply means that once the temperature increases, once the temperature of your module increases, it reduces the voltage, and once the voltage reduces, it also reduces the power output. Okay, so that's just the simple explanation to that. And what this temperature coefficient is now trying to tell us that, for every rise in temperature, this is the amount of power you're going to lose. That's what temperature coefficient is trying to tell us. For every increase in voltage, This is the voltage drop, okay, that is going to result in that, okay. Now, the reason why I'm saying all of this, because sometimes when you pick up your solar panel, I don't know if you have taken the time to look at the label, all those stickers that you see on your solar panel, you will see all of these terms that I'm trying to talk about. You see VOC, that is open circuit voltage. You will see the ISC, short circuit current. You will see the MPPT. You see all of these things I'm talking about. I want, for some of us who are not already familiar with this, I want you, after this class, just go and pick any solar panel, look behind it, look at the label, look at the data sheet. You're going to see all of this, and you need to understand what they mean. And that is part of what we are trying to achieve through this course, to make you understand, because those things are not there for design sake. They are there to communicate, to make you understand, what solar panel, the features and the output of the solar panel, right? So now we're talking about the temperature coefficient, and I told you that it is just an indication to tell us, how much of power we're going to lose for every rise in temperature, right? So the model data sheet gives temperature coefficient for open circuit voltage under standard test, and of course the rate at the maximum power point. So the voltage temperature coefficient is the most common used. Now, inverters and other devices such as the charge controllers can be damaged by modules or string voltage that exceed the specified input voltage of these inverters and other devices. Conversely, if the voltage is too low, this can cause systems underperformance. Now, all these are just pictures based on some of the things I've already explained. Now, voltage temperature coefficients. Voltage temperature coefficients are given in the form of minus 0.156 voltage per degree temperature. So what this simply means, if you look at some of the model, you will see this, and what this simply means that for every rise in temperature, this is the voltage you're going to lose. So if you're calculating your power output, so that you don't go and buy a solar panel that is rated 300 and you install it and it's giving you, for example, you're getting 150 and the sun is fully out, just so that you can understand, some of the factors that are actually reducing your power output and how those factors are also affected. So that's why they provide some of this detail. For every rise in temperature, you lose 0.15 volts. So this voltage can also come in different forms. So it can come in millivolts. So for every rise in temperature, you could lose minus 156 millivolts, depending on the the size. So it could also come as a result of in the form of percentage. So it could also come in the form of, for every rise in temperature, you lose minus 0.36% of the voltage, of the standard voltage, right? So like I said, this is just to help us understand how much we're going to lose for every rise in temperature. There is also current temperature coefficients, right? So for every rise in temperature, how much current you're going to gain, okay? So when the temperature increases, you gain current, but you lose voltage, but you lose significantly on voltage. The current gain is insignificant, it's just small, but you lose more on voltage. And that's why the rise in temperature significantly affects your voltage and it reduces your power output. So this is just a calculation exercise, I think I will just walk us through this. So assume the following data. The yearly daytime temperature of a location ranges from -10. Apparently, this is not Nigeria, okay? But to have -10. So -10, that is the lowest temperature you can get. And then, of course, it moves from -10 to plus 45 degrees centigrade. So a PV module is being installed, which has the following. Now, this PV module, at a standard, the open circuit voltage at standard test condition is 43.24 volts. Open circuit voltage, meaning that current is 0, right? Now, when the current and the voltage is at maximum power point, the voltage will now drop at 35.35 volts, okay? Now, the temperature coefficient is minus 0.168, the large value, fraction there, right? So that's the open circuit voltage, So for every rise in temperature, this is the voltage that you lose. Okay. Now note, the temperature coefficient, that is temperature coefficient at the maximum power point is slightly different than the open circuit voltage. In this case, for the calculations, the difference will be neglected. Now, this means that for every rise in for every degree centigrade temperature drop below 25 degrees centigrade, the module voltage will rise by 0.168636. Similarly, for every temperature rise above 25 degrees centigrade, the module voltage will drop. I think I've explained this already. Okay. Now, let me also make us understand that when you have a circuit, because in the electrical system, when you have a circuit that does not have any load connected to it, the voltage is always high. But once you connect a load to it, you notice that the voltage will drop, right? Now, that is exactly what is happening here. If you look at this open circuit voltage, this means that current is zero, meaning that there's no load on it. And that's when you have a maximum voltage at an open circuit. But when you now have a load connected to it, okay, and now that load is operating at the maximum power point of the solar panel, the voltage will ultimately drop, right? Now, this drop can also, be as a result of the temperature rise, which is what this, section is trying to make us understand. Not necessarily because of the load, but because of the, rise in temperature. I don't know if we have all the time, but I will just walk us through this calculation. So the question is, what will be the maximum open circuit voltage produced by the module? Okay. Now it's still talking about these details that we have here. It's still talking about this this module, the module that have these specifications, right? Now it's asking us what will be the maximum open circuit voltage produced by the module. Now the maximum open circuit voltage will be produced at the lowest ambient temperature. Remember that the voltage is highest at the lowest temperature, correct? So this one is a no-brainer, it's just a straightforward, right? So the lowest cell temperature will be -10. Okay, so at -10, open circuit voltage at -10 is equal to, now what is the, remember that our okay, now what we will actually want to calculate here is the open circuit voltage, right, at -10. Now the maximum power point voltage is 43.25 volts. That is the maximum power point voltage, right? Now we are going to now do plus the voltage gain when the temperature drops. The voltage that will be gained when the temperature drops. Now that's at that standard test condition. Let me just go back to this so that you can understand. Okay, the 43.24 is open circuit voltage at standard test condition. This terminology sometimes might look a little bit confusing, and I'm trying to put it in a best way where we can actually get it, but this will be shared. Now, the open circuit voltage is 43.24 at standard test condition. Now, the question is asking us to -10. What would be the open circuit voltage? So we already know that the open circuit voltage is 43.24, right? Now, when the temperature goes to -10, what would it be? So the standard test condition is 25 degrees centigrade minus -10 times 0. So this is the voltage gain for every temperature reduction, every drop in temperature. This is the voltage that is going to gain. If the temperature is increasing, it's going to be minus. I mean, it's going to be reduction, but because the voltage, the temperature is reducing, so we are going to have voltage gain, right? So when you now do 25 minus -10, what this simply gives you is plus. Minus is plus, based on the mathematics that we know, right? So if you punch this on your calculator, if you do 43.24 plus 25 degrees centigrade minus 10, of course, this will give you plus. You times it by 0.1686, okay? You're going to get 49.16. Remember, at the standard temperature of 25 degrees centigrade, the open circuit voltage was 43. But because the temperature has reduced to minus 10, that voltage has now increased to 49. I don't know if this makes sense. So essentially what we try to do here is that we want to know what is going to be the voltage gain because of reduction in temperature. That is essentially what we're trying to calculate. Once the temperature moves from 25 degrees centigrade to minus 10, how much voltage are we going to gain? That is just it. And then this is another question. What will be the maximum voltage? That is at MPP, okay? What will be the maximum voltage when the module is operating at its maximum power point, that is full sun, produced by the module? Now, the maximum voltage is going to happen at 10 degrees centigrade, minus 10 degrees centigrade, right? Now, what we are giving before, we are giving the MPP, the voltage at MPP. The voltage at MPP is 35.35 at standard test conditions. So, sorry, I'm swiping back and forth, and I know that might kind of be a little bit confusing, right? But this 35.35 is the standard voltage, or the maximum voltage at standard test condition, which we are already given. Now, the voltage gain at that point, because the temperature has reduced, it didn't increase, it has reduced. So we're going to have an increase in the voltage, okay? It's still going to be 25 degrees centigrade minus 10 degrees centigrade times the voltage drop at every degree rise in temperature, which is 0.1686. Now, when we do that, we're going to have 41.25, you know? Now, this used to be 35.35. But because the temperature has dropped, we are able to achieve a voltage gain of up to 41.25. So essentially what this is saying, what is the voltage of the solar panel when the temperature drops from 25 degrees centigrade to minus 10 degrees centigrade? What is going to be the maximum power point voltage? That is just the question. And the same thing goes for the next question. What will be the minimum open circuit voltage? Now, the minimum is going to be when the temperature is highest. You remember here we did for minus 10. So in this case now, it's going to be when the temperature is highest, which is what's the highest temperature there? 70. Based on the question that the data that we had, the highest temperature was 45. The highest temperature that we had was 45, right? But again, 45 is the temperature of, the temperature of the module, right? But in this case now, we have to account for the standard test temperature. So what this means that the temperature was already 25, then it now has to move now to another 45, right? So in that case, you're going to have 45 plus 25. That's how we got 70 degrees here. I think that explains. So the minimum open circuit voltage will be produced at the highest ambient temperature of 45 degrees centigrade, but the cell temperature of rooftop or open field PV system can be 25 degrees centigrade higher than the ambient temperature. So this will now lead to 70 degrees centigrade. So if you now consider the temperature to be 70 degrees centigrade and you factor that into your calculation, then the final open circuit voltage, now this is the worst case scenario, will be 35.65. That is the worst case scenario, you know. But let us not dwell so much on this. I'm sure we might not be dealing with all of this calculation during our installation, but I just did this, presented it just so that we can understand what some of those terminologies means and how to use them in any calculation that you want to do. let us come down to the orientation and inclination angle. I think I'll be very brief about it so that I can round up. So the PV module's orientation and inclination, when we talk about inclination, we're also talking about the tilt angle. So for most of us, we're already used to tilt angle. It's the same thing as inclination. So both the orientation and inclination affect the amount of irradiation that the surface receives, and hence the amount of energy that the module can produce. Now, in the northern hemisphere, when I say northern hemisphere, I don't mean the north, south, east, and west of Nigeria. Now, the entire world is divided at the equator, so between the northern hemisphere and the southern hemisphere. The entire world is divided at the equator. And then you have the northern hemisphere and you have the southern hemisphere. It's different from the north, south, east, and west that we have in Nigeria. Okay. So in the northern hemisphere, the PV module should be facing south. Now, Nigeria is at the northern hemisphere. Remember, I told you that the entire world, okay, one side is the northern hemisphere and the other side is the southern hemisphere. Now, Nigeria is on the northern hemisphere. So for the fact that Nigeria is on the northern hemisphere, PV modules should be facing south. That is how you're going to get the maximum power, from the sun. As long as you're not using tracker. Remember, we're not using tracker, so it's a fixed, installation you're doing. So to get the maximum yield from your PV system, it is always good that you face south, and that's why if you want to do an installation, it's either you go with compass, or most of these smartphones, they have compass, and then you can identify where the south is. Try as much as possible to put your PV panel to be facing south, right? So if it's facing south, you can get the best out of the sun parts. That's what it simply means. But if you're in the southern hemisphere, then your PV module should be facing north, right? So now in the southern hemisphere, it should be facing north, like I just said. This guarantees the maximum irradiation level on the PV module throughout the year. In regions close to the equator, the orientation is less important. So remember, I said that at the center, it is divided. You have the northern, I think I have a diagram that illustrates this. I'm going to come to that. Now, the optimum tilt angle. Now, let's talk about tilt angle. Now, we've talked about orientation. Orientation means the facing, how you face your PV module. Now, let's talk about tilt angle. Now, the optimum tilt angle of a PV module depends strongly on the location. There's no universal tilt angle for PV installation. It depends on the location. So as a rule of thumb, the module should be tilted to an angle that is equal to the latitude of the installation site. So when you go to any installation, the question is going to be, what is the latitude of that site that you want to do an installation? So Nigeria is situated in the northern hemisphere, and the latitude of our Nigeria, based on our location, is between 4 degrees to 14 degrees. That's our latitude. So what that simply means that if you want to do PV installation in Nigeria, you can make it between this range, right? 20 degrees is still acceptable, but if you begin to go above 20 degrees, I don't know why it has to go beyond 20 degrees, okay? But Nigeria is somehow closer to the equator, and that's why you're seeing that Nigeria. Now, if you move down to the south, I think if you move down to the southern Nigeria, that's where you begin to have about 4 degrees. But if you move up to the northern part of Nigeria, then the latitude begins to increase up until 14. But overall, Nigeria is between 4 and 14 degree latitude. Now, roof-mounted PV modules are usually simply installed at the same angle as the roof, since the extra cost of adjusting the tilt angle exceeds the benefit of the extra energy that will be generated. So if you want to do an installation and you're doing it on the roof, and the roof already has a tilt angle, you cannot go and tell the owner of the house that you can't change his roof because it does not conform to your tilt angle of the solar panel you want to do. You just simply have to install it on the roof, okay? Because the cost of there's another option of maybe using angular support. You can use angular support if it is cost viable. You can use angular support because some of the houses that we have these days, you have all this, this modern roof that is, almost vertical, not vertical, but it's almost vertical. When you have installation in such roof, the yield is going to reduce because of the tilt angle of the roof, right? But you cannot ask the owner of the house to go and change the roof of his house because you want to achieve optimum tilt angle. Okay, so you just have to install it that way, or if it's cost viable, if you can use angular support, fine and good. So roof-mounted models are usually simple. Okay, I think I've talked about this. Now, in regions close to the equator, Nigeria is also close to the equator. The most solar irradiation is captured if this PV module is flat. If the country is, or your site installation is on the equator, then you can simply make your solar installation to be flat. However, in practice, a minimum tilt angle of 10 to 15 is recommended to allow for self-cleaning. Now, this is just to illustrate the equator that I talked about. Okay. Now, here, this is the equator, right? And all of this side is the southern part of the equator, and all of this side is the northern part of the equator. So Nigeria is located somewhere here, just somewhere here, So, and that's why our latitude is 4 and 14. We are closer to the equator. We are not on the equator, but we're closer to the equator. So our solar panels should be facing south, southern part of the equator. Okay, so this is just to illustrate that. Now let's talk about solar yield. Solar yield estimation. How do you calculate energy production from your solar panel? Now, in order to assess the energy yield of a PV system, one has to know about the available resource to the PV system, meaning the solar irradiation. There are a few ways anyway to do this, to do the solar yield calculation. So most of these softwares, what they actually use is they use solar irradiation, So if they know the solar irradiation per meter square of the place, and they know the efficiency of the solar panel or the solar module, then they can be able to calculate the yield of that solar system. But there's another way to do this. Let me quickly move. So the economic feasibility of PV plants critically depends on its electricity yield, which in turn depends on both the meteorological condition at the location and the performance of the plant itself. As the electricity yield is heavily dependent on solar irradiation level, it is essential that the accurate and long-term climate data are available for the given location. Solar irradiation at a site is often stated in terms of the peak sun hour over a certain period. Furthermore, component quality, plant design, and layout are, as well as the maintenance plan, will affect the performance and consequently the energy use of the plant. So let us look at performance ratio. What is performance ratio? Remember when I told you that if a solar PV is rated, for example, 300 watts, that 300 watts peak is at a standard test condition, right? Now that is a factory label at standard test condition. Now when you install that solar panel, you might not get 300 watts. So the difference between that 300 watt and what you actually got over a period of time is what we know as performance ratio. Some PV system might be performing at 65% ratio performance ratio. What that simply means that they are performing at 65% of their standard test condition rate. Okay, so there's a formula to do that. So performance ratio is equal to the actual output. The actual output is that after you've done the installation, what is actual output? This actual output can be in terms of energy. So you can say, okay, you install the solar system, for example, for 1 year, and for that 1 year, this is the amount of energy that you've generated from this solar system. Okay, now that is actual output. Now, what is the theoretical output? So assuming that solar system was performing at standard test condition, which it was rated 300 watts, for example, what should have been the output? So when you do this division, you can easily get your performance ratio. So it is determined by monitoring the actual plant output over a defined period, maybe 1 year, and dividing this by the nominal plant output in that same period. The PR, or performance ratio, will change. It will change from period to period, depending on environmental and technical conditions at the plant. A low PR or a low performance ratio is indicative of high system losses. For example, due to high module temperature, reflection of the solar irradiation from the modules, soiling of the front glass, shading. It could also be as a component failure. So there could be so many factors that will actually reduce your performance ratio. So in contrast, performance ratio is also used with common references, with common reference value in the planning stage of a PVC. So if you're at the design stage, how can you now say, okay, this is what this PV should generate? So for example, a performance ratio of 0.75 to 0.80 is used for grid connected PV plant. So if you're designing a grid connected PV plant, you can, so these are assumptions, right? You can only say for certainty your performance ratio when your plant has operated for some certain period. You can say, okay, this is the performance ratio of my plant, of my solar system, right? Now, at the design stage, you can actually make some assumption. And if you're doing a grid connected solar PV system, it is recommended that you use a performance ratio of 75 to 80%, right? Now, then if you're doing an off-grid system, for example, a PR of 75 to 80 is used for grid connected PV system. And then if you're doing for an off-grid system, it is recommended that you can use 65% for an off-grid system. Now, these are assumptions at your design level, right? You can decide to use 70 if you choose, or you can decide to use 75 if you want to, but I will want to keep it at best 75. You know, I would not encourage you that you go above so that you don't overestimate. That's the reason why I will recommend that 75 at maximum. So this means that the expected gross energy production potential will have to be multiplied by the performance ratio or reduced by 1 minus the performance ratio to reflect the expected production after system losses. Once the energy yield of the PV system has been established, the revenue from electricity sales can then be calculated in order to evaluate the profitability of the system. I want us to know that when you're doing a PV installation, especially when you're doing it for business, or you want to make presentation for businesses, what are more important is how much electricity they're going to get out of it. All of these technical jargons, your client may not be interested. In the end, they want to know how much electricity am I going to get? How does it differ from my current source, from my current technology? So if your client is using diesel generator and the grid, and you're coming to present solar system, in the end, is going to be interested, can this solar system, can it meet my energy demand? At what cost, right? So these are the calculations that you need to do. Sometimes softwares can also help you do these calculations. Now, I want us to talk about one important concept. I think we'll be writing up shortly. One important concept is energy. So we'll talk about peak sun hour. So the following equation provides a quick and simple way to estimate energy yield of a PV plant over a particular period of time. Now, one important concept I would like us to talk about is peak sun hour. This is PSH, peak sun hour. Okay. Now, peak sun hour is, you remember when I talked about standard test condition, and I told that the standard test condition of a solar panel is 1,000 watts per meter square. That is the standard test condition. But when the sun comes out, it is not at one, can be at 200 watts per meter square. It can be at 400 watts per meter square. Even at peak, it can be at 800 watts per meter square. So it actually does not get to 1,000. In some cases, sometimes it might get to 1,000 watts per meter square, right? Now, and the sun comes out in the morning, it goes and it peaks around afternoon, around noon time, and then by evening, it begins to drop, right? Okay, let me use this. I'll go back to another example. Let me use this to explain it. So let me just explain what the peak sun hour means, because it kind of creates some level of controversies anytime I bring this up. I was in one of the class and I said that if you're doing your design, you should consider a peak sun hour of 4 or 5. And somebody said, no, that the sun comes out in the morning and it stays till around 4 or 5 in the evening. It cannot be 4 or 5 hours. I said, okay, that's not what I mean. Let me explain. Now, this is when the sun comes out. I don't know if I need to zoom this for some of us that okay, so when the sun comes out, it gradually gets to the peak and it gradually comes down, right? No, in all of this, it did not hit 1,000 watts per meter square, right? So peak sun hour is now trying to compress all of this. push everything together and make it get to 1,000 watts per meter square, right? And then how long, if the sun, assuming the sun comes out in that morning and it's already 1,000 watts per meter square, and it maintains that 1,000 watts per meter square, how long is it going to stay? So all this shaded area, all this time that the sun was out, assuming that it maintains a 1,000 watt per meter square, how long will it stay? That is what peak sun hour actually means. Okay, so when you compress all of this, meaning that the height will increase further, but the length, this length will now compress, right? This is what you're going to get. Okay, and when you do this, you're going to likely get about 4 hours. So in Nigeria, peak sun hour is between 4 to 5 hours. Right? If you go above that, then you're being overambitious, right? But between 4 to 5 hours. If you're going down south, it moves around to 4 because of the the kind of weather. If you're going up north, you can, from the middle belt up north, you can increase to about 5 hours. So that's what essentially peak sun hour means. So let me go back to this example. So so this is the formula for calculating the energy yield. So energy yield is equal to peak sun hours times peak of your solar module. So if your solar module is 300 watts, 300 watt peak, then that is what you're going to put here. Then times the performance ratio. I've talked about what performance ratio is, and I've also explained what peak sun hour is. And then this peak of your solar is your installation capacity of your solar system. And that's how you calculate your energy yield. So this is, the E is energy yield of the PV plant over a period of time. The PSH is the peak sun hour. I've explained that. The peak, P peak, I've also explained that. And the performance ratio, I've explained that. So that is one way to do your energy yield estimation. Another way to do your energy yield estimation is when you know the irradiance of the particular place. If you know the irradiance and you know the efficiency of the solar panel, you can multiply them out and you can get your energy yield. But those ones, you might need more effort to be able to determine this, and you don't know the efficiency of the solar panel that the developer is actually going to use. Assuming that you're not always going to do the installation, maybe you're just a designer, you want to design the system and you want to calculate how much energy, how much of energy yield you're going to get. So you can use this formula that I'm presenting to you. So I've explained what the peak sun hour is. Let's also look at an example. So a power plant developer is planning 2 PV plants, one in the Northern Europe and the other in the Southern US. And he wants to estimate the energy yield of each of the plants to gauge their economic feasibility. Now, the system that is going to install in the Northern Europe, these are the system characteristics. The rated power output is going to be 1,000 watts peak. That is capacity of the solar PV. The peak sun hour of Northern Europe, now this is for an entire year. The peak sun hour for an entire year is 1,200. Okay. The performance ratio is going to be 0.8. That's 80%, right? Now, if you want to calculate the energy yield in Europe will be peak sun hour times the peak capacity of the system times your performance ratio. So we know the hour of operation, which is 1,200 200 hours. That is your peak sun hour times your watt peak times your performance ratio. So for that year, you're going to get 960 kilowatts per annum. That's what you're going to get. Now, if you do this same installation in the Southern USA, okay? Now, in Southern USA, the peak sun hour is 1,900. So meaning that the sun is more in Southern USA, right? But the same capacity of solar installation. But again, because of the high sun that is out in the Southern USA, it also reduces the temperature. So the performance ratio reduces slightly. Instead of 0.8 or 80%, you're now using 70%. Now, to calculate the energy yield in the Southern USA, you're going to use the peak sun hour times the peak capacity times the performance ratio. And when you do this, you're going to have 1,330 kilowatt hour per annum. Now, if you are an investor and you have a choice to choose where to make this investment, whether to invest in Northern Europe or to invest in Southern USA, where would you make your investment? I need at least
Southern
one
USA.
response. Okay, perfect. Because you're going to actually get more yield from that point because of the availability of the sun. They have a wider peak sun hour, and because of that, you can actually have more yield. And then when you have more yield, they can make more money. And that is some of the feasibility studies that you do when you're designing a solar system. It also happens in Nigeria. Sometimes you look at systems in the
Hello, am I the only one not hearing you? You don't seem to hear again.
Yes, I can hear him too.
Maybe his audio has gone off.
It seems he's disconnected.
All
Maybe
right.
we got timed out. It's over 2 hours now.
Okay. All right. It's possible. But this can happen. Okay, that's it.
I believe it's more of network.
I believe so.
I guess yes, since we are not
I
been
think it's
disconnected. I believe it's not. It's like he's back. Oh, his network his mic is muted. Your mic is muted, sir. Jima.
So only two of them are out. Therefore, I believe they have timed up. Thank you.
well, I think it is time, except that we need to round up properly. Except it's going to repeat this again.
That's it.
My experience with the company is more of network.
But his mic is muted. His mic is muted and the screen is not showing again. Before the screen remain, but his mic is muted.
We should have ended properly. I don't know.
Mm.
Maybe his own side is timed out. Maybe that's why it's not coming on again, or it's network problem. I mean, let me coach, I'm trying to join back, but I've not been letting already. Of course, you should have transferred the admin to someone else. I don't know. So the person should be able to admit the packet.
Okay. So should we continue to wait?
Just hold on, let me, just ask anyone who has the admin should let me, but I'm waiting.
Okay. Does anybody have the admin? I'm not sure. It should either be between you and Engineer Uche.
Okay, let me speak to you now today.
All right. Thanks.
Thank you.
Okay, sir, you were the one that wanted to put me through on the commercial and industrial. On Petty when you come back, please. Can we discuss that? Hello.
Yeah, I'm not the one.
Okay, there is one of our engineers in this platform that was trying to direct something at the level of introduction. Are you getting me right? About although somebody have asked using Homer software for simulation based on what you do as input and some other things. Some of these projects, when you go to field, I've been practicing some of them in the field. I've had training on this before this other one. There are some of the challenges we face, more especially in the area of material selection, the inverters, the panels itself, and the batteries at times. Although in panel, I normally choose Jinko.
My apologies. My apologies. I don't know. Somehow I was logged out and I was trying to get back. I have to, call the generation to admit because I was waiting, hoping that somebody would admit me in. I have to call in generation to do that. Engineer Uche, if you can hear me, please, I need access to share so I can just conclude.
There are many chimers now. I don't know. Okay, I don't know which one is you.
My apologies. I don't know. It seems
okay,
I shared the link on the platform and so many people
making noise.
With the link and they're all having.
I'm making you the host now, so I can end it when you are done.
Okay. I'm almost running off because we have already fast spent our time.
Okay.
But I'm almost on the last slide. Yeah, I'm on the last.
Remember,
slide.
Once you are done, close the recording so that you not ask questions, please. It doesn't become too heavy.
Okay, that's fine. Thank you. So this was where I was knocked out. But I was only trying to explain that if you want to do a solar system, it's always good that you understand the nature of the load that you're trying to power. And that essentially means the consumption pattern from morning till night across around the clock, just so that you're sure that your system can meet their requirement at the time they want it. Some may say, okay, we don't want nighttime consumption, we only want daytime consumption. So you have to design to meet that requirement. But
The audio is off again. We are no more hearing you again.
Hello?
I think he has been locked out again.
I think so. Yeah, you've been locked out again. No? I hope you do.
Yeah, I think let's just end the class now. Let's end to end. Everyone can. I was hoping to end the class. Now I'm already at the last slide. I don't know. My internet has just become very unstable.
Okay. All right then.
Yeah.
Thanks, yeah. Bye.
We'll continue next Friday. I'm just at the last slide anyway.
Okay. Is today not the last day?
No. Today is not the last day.
Okay, it's next Saturday.
Yeah.
Okay,
Yes,
next.
Saturday.
Okay.
But before you go, sir, I was talking about Homer. When are you going to give us training on Homer? Because that is very critical. Having learned all this, we should be able to use our hands and do a little bit of designs.
Yeah, that will come. Yeah, we'll arrange for that.
Mm-hmm.
I'll let you know.
Yeah. Thank you very much.
All right.
We are grateful. Bye-bye.
Bye.
Okay, goodbye, everybody.
Goodbye. Thank you so much.
All right, thank you so much.
Cheers.
Thank you so much.
Appreciate it.
We appreciate.
Thank you, Engineer Shima. God bless you.
Mm.